In this video, we are going to learn about the least square estimators in our regression models. We have another video on the curve fitting, and we learned about the simple linear least square regressions. So it's not a bad idea that if you go and watch that one first before starting to work on this one. In that video, we learned that how can we find out the parameters through least square methods. In our regression models. Regression model means that we are gonna find out the relation between variables. For example, consider a distillation column. We have temperature and pressure. So knowing the relation between this temperature and pressure is gonna help us to make a better decision on our, let's say, operating condition. Another example would be, for example, think about the fossil fuel consumption. So when we have more fossil fuel, in that case, we are going to have more greenhouse gases emission as well. So all of these things, we can show them with the empirical models, and we can use the regression model analysis to find out that, okay, so what would be the exact relation between these variables. So let's look at here. Here I have the, let's say, fossil fuel consumption. And here I would have the greenhouse gases emission. Okay. So when I look at this, it's like that. I know that if I consume more fossil fuel, I'm going to have more greenhouse gases, right? So let's say, I would say I have one point here, like with the relation. I'm going to name this one X and this one Y. So let's say I have like a few points. Okay? So with regression model, in fact, we want to find the regression line which would represent these data forms. With the least square method, we try to find out the best regression line. So we said that, okay, so let's have this one as our line. Let's have a line like this, right? And let's assume that this is the best fitted model, right? So these are all of these points are our data points, and whatever you get on this line is going to be your predicted value. So we call this one regression line, which gives us the predicted values that we would have, right? And then let's say we would say y is equal to beta 0 plus beta 1 x plus some e or epsilon. So with this one, in some books, instead of beta 0 and beta 1, they would use the alpha 0 and alpha 1. It doesn't matter, as long as we want to find out the parameters of this model, right? So in the other video that we had with the least square method, we found the equation for these ones. In this video, we are going to learn about the sum of the squares of the residual, of our regression, of the x and y, deviation of the mean from x and y, all of these ones, because we want to make a shortcut in our calculation. Whenever we are working with the large sample size, the equations that we are going to learn in this video is going to be more helpful for us. They're simpler when we are working with them. Okay, so when you're looking at this one, this y was our greenhouse gases emission, like we would say our output, right? This x is our fossil fuel consumption, and which we would call it regressor or our predictor, right? Is a variable. This e is our residual or error. So I'm gonna write down here, this is my regressor, and this one is going to be my residual or error. Okay. In the method of the sum of a square, what we have done so far is that we said that let's write down this error, right? So we said error is equal to the y minus beta null minus beta 1x. And then when you look at it, so look at here, this is my predicted value, right? So this amount, if I found the beta null and beta 1, if I have an estimate for it, like if I make this one as estimation, hat means estimate, right? So in that case, this amount is going to be my predicted values. So it's like that E is going to be equal to observed value minus the predicted value. So if I want to show it here, what's going to be? Let me just move this one a little bit. Okay. So when we look at here, it's, if you want to transfer it on this one, it's going to be, look at here. So I have this one. This amount is the observed value minus the predicted value, which would be here. And then this amount, this amount, this amount, and this amount. So I want to make a model that these values, if I add them, it will be the minimum because these are error, right? So I want to have a model which has the minimum amount of the error. So what would I do? I would say that, and because these ones going to be like deviation is going to be negative and positive, we are going to get the sum of the square of them. So we would say that like the sum of the square of the error, so sum of a squared error, right? And it's equal to the sigma, this E, which was error, I'm going to say EI, and I is equal to 1 to n. Like if I have n data points, I'm going to have the, like, here is 5 data points. So n is going to be equal to the 5. It means that what would be the size of your sample? So I have the sum of the square of error equal to sigma, I equal to 1 to n. With this one, if I want to write it down in the form of the y, so what's going to be? Instead of sum of a square, from now on, I'm going to put ss. So it would be ss of error equal to sigma. This ei, what's this? Is the y, right? Minus y estimate. So it's going to be y minus y estimate power 2, because it's the square of it, right? So it's like that, and it's going to be for I equal to 1 to n, for when we want to write it down for each of these data points. So this is going to be the sum of the square of the error, and we had it in the previous video as well. Now we want to find out, we want to define a few more sum of a square, and then find out beta null and beta 1 based on those sum of the squares. So that's the main objective of this video. So it's like that, we have the sum of the square of the error. It's going to be y minus y estimate power 2. I can write down I equal to 1 to n, and it's the yi in this, and this one is the y estimate I, right? For each of these data points we are going to have. The next thing is the sum of a squared of the, like, due to the regression. So I would say, because this is my regression line, so I would write down sum of a square due to the regression equal to the. So for this one, we would say that is equal to the y estimate minus the mean value of the y. So the reason that we would say the mean value of the y is that y is our observed data, right? And the average of that observed data would be the closest value to the reality when we want to work with the regression. So sum of the square of the regression, we would say is equal to the sigma, and then I would write down the value of my regression, y estimate, right, minus y bar power 2. So this one has I, but this one is the y bar. Y bar is like sigma y divided by n. So this is going to be sum of the square of the regression. The next thing that we want to find out is that we want to find out what's going to be the sum of the square for the x and y. So look at here and this graph. Let me get another color. Okay. This is y, right? So when this is y, we can say that, let's say this is going to be my y bar, the value of the y bar. For the regression line, we said that our estimate minus y bar, like the deviation, is going to give me the sum of the square of the regression. So for the sum of the square of y, we have very similar situation. So we would say s sum of the square of y is equal to the sigma. So here, think about it for a moment and like pause the video and think about it for a moment, that how, if this sum of the square of r is equal to this, what's going to be this one, and then come back to and listen to the rest of it. So SSY, and in some books they show it by SYY as well. So I can write it down SYY. So SYY or SSY, sum of the square for the y, is going to be sigma, our y minus y mean value for the y. So it's going to be whatever observation that we have minus y bar square. So that's going to be sum of the square for the y. In the regression analysis, this one is equal to the sum of the square of total as well, because it's comparing our observations, right? The deviation of the observation from the mean. And because of that, it's going to be sum of the square of total. So I can write it down, this one here, it's equal to the sum of the square of total. Okay. We have two more sum of the square for this one. One is that, so we found that sum of the square of the y. What about the sum of the square of x? Because we have x value as well, right? So which was, in this example, is the fossil fuel consumption. So I would say, I'm going to stay with this one. Sum of the square of x, it's equal to the. So it's very similar to the y one. I just write down xi minus x bar square of it. So in fact, it's going to give me the sum of a square of the deviation of x, each of the x of the observation from the mean. Okay, we have one more sum of a square that we need to find out, and it's that sum of a square of the xy. So I would write down here, sum of a square of the xy is equal to the sigma. So I need to consider the deviation of x from the mean of the x, and also the deviation of the y from the mean of the y. So what's going to be? It's going to be like xi minus x bar times yi minus y bar. So that's going to be my sum of a square of the xy. So far we know the 5 different sum of the squares, and all of them, it means that you are going to get the difference and find out the square of it and then add them together. So it's very simple when you look at it this way. So in the next step, we want to write down our parameters based on these sum of the squares. As I said in the video, that it was like the name of it was simple linear least square regression, as one of the categories of the curve fitting. So in that one, we learned what would be the equation of these ones. Like it had a long equation and that we had. So for these ones, based on these SS, we can find out the beta null and beta 1 like very easy, in a very easy way. So I would say, and beta null is my intercept, beta 1 is a slope, right? So I would say let's say beta 1 is equal to. So I want to work with the sum of a square, so I would say it's equal to sum of a square of the xy divided by the sum of a square of the xs. So sum of a square of the xy divided by sum of a square of the xx. So that's going to be my beta 1. This is my beta 1 estimate. My expectation for this beta 1, so it's like this. And then I would have expectation for beta 1, right? So beta 1 estimate, it would be beta 1. And then the variance for this beta 1, if you're very interested to find out the variance of this one, it's going to be equal to whatever variance that we have in general, like sigma 2, or the estimate of that, divided by the x, like sum of the square of the x. So that's for the slope. The next one is for the intercept. So for the intercept, we are going to do exactly the same things that we did for the in the previous video. So it's beta null estimate. I would say it's equal to the y bar minus beta 1 x bar. So it's like that. We are going to use this equation. So it's going to be y bar minus beta 1 estimate x bar. So for beta 1 estimate, we are going to put down this value, y bar and x bar. We know the value of it, so we can find it easy. The next thing that we want to do for the beta null is the expected value of the beta null estimate and also the variance of it. For the expected value, for the beta null estimate, it's going to be equal to the beta null. Right? And for the variance of it, the equation it's a little like longer than the equation that we have for the variance of the beta 1. So it's going to be the variance of the beta null estimate. It's equal to, I'm going to write it down here. It's going to be equal to we have the sigma 2. And then we are going to have the 1 over n plus x bar power 2 divided by s of the xs. So it's going to be times 1 over n plus x bar power 2 divided by sxx. The reason that we need to know these variances is that later, when we want to, in another video, when we want to learn about the confidence intervals of these beta estimates and like different beta that we have, the estimates of them. So we will need to work with these variances. So we have the variance, so we can find out the standard deviation of it. So that's the beta null and beta 1. The next thing is that, okay, so let's say I want to play with these sum of the squares and find out the relation between them to define the coefficient of determination based on these SS. So what I'm going to say, I would say that SS sum of the square of the error, it's equal to the, basically it's like this, sum of the square of the total, I can write it down this way, it can be better. Sum of the square of the total is equal to sum of the square of the error plus sum of the square of the regression. And even when you look at here, it's going to be like this part plus this part, right? The sum of the square of these ones that we are going to have. So from here, I can say sum of the square of the error or residual, it's equal to sum of the square of the total minus sum of the square of the regression. So I would say sum of the square of the error is equal to sum of the square of the total minus sum of the square of the regression. So with this one, when we want to write it down, so we can say, we can define the coefficient of the determination. So I would write down here coefficient of determination. So we had this one in the previous video as well, but it wasn't based on the sum of the squares. So this one is the shortcut for it. So coefficient of determination is the same as the R square, and with the R square we would say that how good our model is, right? How is the goodness like of the fit. So we would say for this one, our R square is equal to sum of a square of the regression divided by the sum of a square of the total. Or if you want to use the sum of a square of the error, you would say it's equal to the 1 minus sum of a square of the error divided by the sum of the square of the total. Okay? So that's the coefficient of the determination. That to say that if our model is good or not. So everything that we have learned here, it's basically, it's a short, as I said, it's a shortcut that we can use for the large sample. If our sample size is small, using this method or the previous method that we had in the other video that I said at the beginning, doesn't like the workload is going to be the same. But with this one, and when we are working with the large sample size, it's gonna make the calculation like half. Because of that, it's a good one. It's a good method to learn it.